Okay, so in this section, we're going to look at applications of all of the different conics we've looked at with the exception of a circle. Okay, we have two parabola applications, one ellipse and one hyperbola. All right, so I've pulled all of these just straight from Delta. Okay, these are our questions straight from Delta. All right, so let's look at the first one here. Says a paraboloid is a 3D shape whose cross sections are parabolas. We've already talked about a paraboloid. The way we looked at it was we took a two-dimensional parabola and we rotated it around its axis of symmetry in order to create the paraboloid, right? Now here they're saying the paraboloid is a 3D shape whose cross sections are parabolas. You'll learn more about cross sections in calculus, but basically just think if I took a paraboloid, which if you look at the picture here, the spotlight, the dish there is the paraboloid part of it. If I took that dish and I just cut it in small slices and I looked at those from the side view, those would be cross sections that look like parabolas. So that's what that means when it says cross sections are parabolas. Okay, so it says the spotlight has a reflector in the shape of a paraboloid with a bulb located at the focus. Right there, that's key. Bulb located at the focus. Okay, we have a cross section of the reflector modeled by the parabola that's shown in the drawing there. They have it positioned so that it's opening to the right with the vertex at the origin. Okay, nice to put it at the origin so that we don't have to mess around with different H and K values. Okay, so it says the reflector's bulb's placed 3.5 inches from its base. What's the equation of the parabola? So the way they have it positioned, it's opening to the right. That would mean our model would have to be y squared equals 4ax, correct? A is supposed to represent the distance from the vertex of the parabola to the focus. Well, they said the bulb is located at the focus, and it says the bulb has been placed 3.5 inches from its base. So that 3.5 is my A value then. So I can substitute that into the model. And 4 times 3.5 would be 14. So the equation is simply y squared equals 14x. That's all we're looking for there. Any questions on that one? All right, next one. Okay, we got another paraboloid. Solar cooker is in the shape of the paraboloid this time. Have you seen these before? A solar cooker? So it's like a reflective dish that you can point towards the sunlight. The rays shine down on the reflective material, and then they bounce up to your focus point, and you put your food at the focus point so that it can cook it. Right? You put like your pot or your pan. So you can kind of see that in the picture there. All right, so it says we have it with the cross section of the solar cooker can be modeled by the parabola shown below. This time they've got an opening upward, and they put the vertex at the origin again. So the model for this one would be x squared equals 4ay. And it says the focal point is 63 centimeters above the base of the cooker. So that would be where you're placing the food, the pot or the pan to cook the food with. Okay? And that 63 would be your A value. So if I substitute that in, what's 4 times 63? 252, right? So there's the equation for the parabola that's graphed there, but now we've got to go further. It says the width of the cooker is 168 centimeters. That means from end to end. We want to know its depth. Okay? So the approach here would be, if we can figure out the y-coordinate of that endpoint using our model, okay? The depth would be the y-coordinate of that. And then what would the x-coordinate of that point be? If the width of the entire dish is 168 centimeters. 84, half the width, right? So that endpoint, we know it has an x-coordinate of 84. We can use that with the equation we just created to come up with the y-coordinate. So I'll go 84 squared equals 252y. 84 squared is 7,056. Then I'm going to divide the 252 over. And we are going to end up with a depth of 28 centimeters. All right, so notice the approach here is make a model, make an equation, and then now use the equation to find your missing value, right? All right, next one. Now we switch over to an ellipse application. An ellipsoid is a 3D shape whose cross sections are ellipses. So here we have a lithotripter or lithotripter. It's a device in the shape of a half ellipsoid. It's used to crush kidney stones with shock waves. So what happens is you have an emitter, you place it at the focus closer to the lithotripter, and then the kidney stone is placed at the other focus. All right, so I'd never heard of one of these before until I saw these show up on this Delta assignment. But here's a picture of a lithotripter. So right here would be like your imaging device that you can use to kind of see where the kidney stone is. Right? You have this monitor attached to it. And then down here in this section would be where the ellipsoid is positioned. So if we kind of zoom in and get an internal perspective of that, this is what it would look like. Half of an ellipsoid, and you place the emitter at one of the focus points of the associated ellipse. That emitter is going to send out shock waves. Those shock waves are going to bounce off the inside of the ellipsoid. And then if you position the patient over here so that the kidney stone is right at the focus on the other side of the ellipse, then those shock waves are going to be directed right over to it and be able to break it up. Okay? And therefore, it would make it a lot easier to pass it and not be as painful, obviously. Okay? So in this situation, it says cross-section of the lithotripter can be modeled by the ellipse shown, centered at the origin with a horizontal major axis. So we're wider than we are tall. So the model for this would have to be x squared over a squared plus y squared over b squared equals 1. Remember, for the ellipse equation, it's not important which variable is first. It's more important on which denominator is bigger, right? And a is supposed to be the biggest value on an ellipse. So if we're wider than we are tall, the a squared value has to go below x squared within our equation. Okay? So they're saying we're placing the emitter 27 centimeters from the vertex of the ellipse. So the emitter is being placed at one of the focus points. So by the picture here, this is where the emitter is. Okay. And then the stone, meaning the kidney stone, is placed 48 centimeters from the emitter. So that would be over here is where the kidney stone is. And now I can use those two numbers of 27 and 48 to reason out my A and my C values. Starting with C, C is supposed to be the distance from the center to your foci, right? Well, if the distance from one focus point to the other is 48, then C's got to be half of that, right? 48 over 2, or 24. A is supposed to be distance from center to the vertices. So how am I going to calculate A here? We know the distance from the center. Yeah, the distance from the center to each focus point is 24, and then you got to go 27 more beyond that to get to the vertex, right? So A is 24 plus 27, or 51. Okay. Now, ultimately, all we're being asked of here is to write the equation of the associated ellipse. So the only other thing we need to make the equation is the b value, or the b squared value. So we pull out our Pythagorean theorem. B squared equals a squared minus c squared for an ellipse. So that's 51 squared minus 24 squared. Let's just do, so 51 squared is 2,601. 24 squared, 576. So we subtract 2,601 minus 576, and there's our b squared value, 2,025. Now I can say the equation for this associated ellipse would be x squared over my a squared value, which is 51 squared, or 2,601, plus y squared over that b squared value, 2,025, and we're equaling 1. Any questions on that example? All right, last one is an application of a hyperbola. Here we have a hyperboloid, is a 3D shape whose cross sections are hyperbolas. And these can show up in nuclear cooling towers. You ever seen these before? Here, one place somewhat locally that comes to mind is Perry, Ohio, up near the lake. Anybody been up there before? Okay, have you been to Perry High School? No? Mason, you remember? Yeah, so Perry High School is right next to a nuclear power plant. Like literally, you can see all of these cooling towers from campus. And my wife's from up that way. She's up from Mentor, and we've always joked that like people that live in Perry, they glow in the dark because of all the radiation they're exposed to, right? Just a joke, right? Okay, so here, the cross-section of the cooling tower can be modeled by the hyperbola shown below. Once again, centered at the origin to make things easy for us, and we've got an opening left and right. So here would be the half that's opening right, Here would be the other half that's opening left. Okay, now they tell us the smallest diameter of the cooling tower is 132 centimeters. So being that it's the smallest diameter, that tells us that 132 is the length of the transverse axis, or the distance between the two vertices, right? Okay. And then we're also told that the diameter is 149.6 meters, and it's at 72 meters above where the center would be, right? So like the top of the cooling tower diameter across is 149.6 meters, and then distance to get up to the top from the center there would be 72, right? So a model for this one would be x squared over a squared minus y squared over b squared equals 1. Are we okay with that? All right, now I can tell you my A value is half of that 132, which is what? 66. Good. Okay, but I also need the B, or B squared value, which the other numbers that I'm given don't directly tell me that. Nothing about the 72 or the 149.6 tell me that those are related to the co-vertices of this, right? So what I'm going to do, though, is use those to come up with coordinates of a couple of the points on the hyperbola itself. So you can do either of the 2 points at the end of the diameter up there at the top. I'm going to do the one over on the right half of the hyperbola. So its x-coordinate would be half of that 149.6. So 74.8. And then the y-coordinate of it would be that 72. So effectively what I've got here is just this random point on the hyperbola with an x-coordinate and a y-coordinate that I can plug into the equation or that model there along with my A value. So we have 74.8 squared over 66 squared minus 72 squared over B squared equals 1. Okay, now I'll do all the squaring. 74.8 to the second is 5,595.04. 66 squared, 4,356. 72 squared, 5,184. Okay, and now I just got to figure out how I can solve this for the b squared there, right? Several different approaches or strategies you could use. Here's going to be the one I'm going to take. I'm essentially going to switch these two terms. I'm going to add 5,184 over b squared to the right, and I'm going to subtract the 1 over. And when I do that, I'll get a common denominator. Okay, so if I subtract the 1 over, I'm going to write it now as 4,356 over 4,356. And that's now going to equal positive 5,184 over b squared. Now I've got the common denominator on the right side that I can use to combine those fractions. That's going to give me 1,239.04 over 4,356 equals 5,184 over b squared. And what I've created here is a proportion, which I can solve, of course, by cross multiplication. So we'll have b squared times 1,239.04 equals 5,184 times 4,356, 225.81504. Divide this out on both sides. Oh, and look at that. Divides quite nicely, actually. 18,225. Okay, so now I've got everything I need to make the overall equation for this. We said again the model was x squared over a squared minus y squared over b squared, right? So x squared over the a squared, which was 4,356, minus y squared over the b squared value we just found, equals 1.